Okay, Engineering 10. Today we're going to learn about pot. The pot that you should be learning about anyway. So in your little baggies, you should see a little blue box, a little blue square with a little white dial in the middle of it. And it's got 3 legs. So that's what your potentiometer is, commonly called pot. And this is the type of pot that you should be playing with. So the learning goals for today are learning how potentiometers work, using them to see how voltage is dispersed through a circuit, and also to see how current is dispersed through a circuit. And we may be able to do a practical application of Ohm's law as well. So what we're going to be doing is trying to recreate your first circuit, except this time, instead of just using a bunch of resistors and swapping them in and out, we're going to use the potentiometer. You should have a 2K or 2000 ohm potentiometer. You'll also need your LED and a multimeter. So first of all, it's kind of hard to test the potentiometer because they've got such small little legs. So I'm going to try and show you what it looks like in Tinkercad here. Okay, here we have our virtual circuit in Tinkercad. For our components here, we've got obviously our breadboard, we've got our potentiometer, and we've got our virtual multimeter, which looks very, very different than the one that you have. It's pretty simple. And there are 3 settings on it. We've got, if you can zoom in on it, you can actually see a little bit better. Maybe we've got our A for amps, we've got our V for volts, and we've got our R for resistance. So when we're doing this, we're going to actually try to be measuring R for resistance. Here's our potentiometer. Potentiometer has 3 different legs. And we've talked about 3-legged components before, but the way that Tinkercad has it labeled is that this one outside leg is terminal 1, the other outside leg is terminal 2, but the middle one is the wiper. So essentially what you can see is the potentiometer, or the pot, is a variable resistor. It varies based on where the dial is set. So I can have it set all the way to 0 ohms of resistance, in which case the current's just flowing straight in one leg and out the wiper and back. Or I can set it up to, in this case, 10,000 ohms of resistance. You can also have a mega ohm potentiometer. You can have all sorts of different resistances in there. So a potentiometer is a variable resistor, and it varies based on where the dial is set. Okay, so once you have that, then the other thing you need to take a look at is how the potentiometer is actually made with 3 legs. Now, if I were to hold up my fingers to you, if I hold up my middle finger, that means something. If I were here, I would be giving you all the middle finger. But imagine that I'm holding up the middle finger to you. You're going to be insulted by that, or at least it's going to mean something. You're either going to laugh or be insulted or something. It's meaningful. The middle leg on almost all electronics devices, when there's a middle leg, it means something as well. And on the pot, the middle leg is called the wiper. That has to be in play. So notice that this potentiometer can be used. All 3 legs can be used, and we'll use that sometimes as well. But for our circuits right now, we're going to start by using only 2 legs. The wiper is always in use. That's the middle leg, because that matters. And then one of those outside legs. Now, which leg doesn't matter, but you can take as long as you remember what it means. If you're using this outside leg, then that means that going this way is going to be at 0 ohms, and going the opposite direction, going clockwise, is going to be at 10K ohms. And if you use this leg over here, let me just change it if I can. Oh, crap. Hold on. Let me just get rid of that entirely, get rid of that entirely. Sometimes Tinkercad is a bit frustrating. Let's go back to this one. Now you've lost what I was saying. Start my simulator. And you can see now this way is at 0 ohms of resistance. And I turn it counterclockwise to get my max, which is 10K. Okay, so now they've figured out what the pot does, now we're going to try and put it to use. So if you are trying to test your pot the way I just did in the virtual world, you might have some issues with it. I don't mind you trying that, but don't waste a lot of time. It's really, really hard to get the probes of your multimeter onto these tiny little legs of the pot. So let's move on. What we're going to try and do now is see what it does when the potentiometer is wired up in series with an LED. You guys are smart. You can probably figure out what's going to happen. But let's see what it does. So first of all, you want to turn the dial so that it's at about the halfway point. If you have it on one end, then there's a good chance you're going to blow your LED, and I don't want you to blow a whole bunch of LEDs. So begin with the pot dialed to the middle. If you have any fingernails whatsoever, you should be able to turn that little dial. If you don't, you may need to find a tiny little slot or flathead screwdriver to be able to get that in there and turn it. Okay, once you do that, you're going to try and build a circuit. So if you take a look at this little diagram, this is a diagram that you could do with alligator clips, but I've taken your alligator clips because I've given you breadboards. So you now love me because breadboards are amazing. They are so much easier to build a circuit with. So let's check it out. I'm going to do this virtually with you on Tinkercad. So I'm going to try and just build the simple circuit. Actually, let's do it this way. Simple circuit with a pot with our 10K ohm resistor. I'm going to use a 9-volt battery instead of a 6-volt battery, and I'm going to use an LED. Okay, so I've got our simple little circuit built here. So what I've done is I've got a 9-volt battery. I've got the positive terminal connected to my breadboard, attached or connected to the anode, the long leg of my LED. So remember, the anode gets power because long legs equal power. Look at Usain Bolt. Usain Bolt has the longest freaking legs, and he's the world's fastest human. Long legs, power. So look for the long leg. The flat side of the LED also indicates the cathode. So that's the short leg. The cathode gets the negative side of the circuit, and I've got that plugged into the breadboard. Notice that I've got both legs plugged into different rows of my breadboard. If you have them plugged into the same row, you're not separating the legs. So power into the anode, cathode connected through the breadboard and through a little tiny jumper wire to the wiper. Remember, the wiper is the leg that matters. That's the middle leg of the pot. And then choose one of the terminals. I've got terminal 2 with one of the outside legs connected back to ground. Okay, so nice little circuit. This is the closed circuit. Current's flowing through here, through here, through here, through the pot, and then back to ground. So let's see what happens when we start the simulation. So notice that I've got my pot set right now, right smack dab in the middle. So I know that's roughly 5,000 or 5K ohms of resistance. So now, I don't know if you can tell this very well because it's hard to tell in the simulator, but my LED is lit. I'm lit right now. It's because of all the pot. Here we go. So now if I turn the dial a little bit more, look at how that LED is getting lit, even more lit, even more lit, even more lit. And then if I turn it the other direction, then it's going all the way to darkness pretty much. Probably in yours it'll actually go dark because 10,000 ohms of resistance on this LED should make or on this pot, should make the LED pretty much dark. Going all the other way, if I go too far, check it out. I just blew my LED because I've just reduced the resistance to 0. Now, if you do this, you're now out an LED and you owe me about 11 cents. If you don't do this, if you're careful, you should not blow your LED, but you should be able to see it dim, like get dimmer and get brighter and get dimmer and get brighter, a little bit more dramatically than this. Okay? So that is how our LED works, our potentiometer works. So if you turn the pot up very, very slowly, you should see the LED getting brighter, and turn it the other direction, you should get it dimmer. You and your little dime bags have 2 LEDs. So now you've blown one. If you've blown one, replace it. Remember to twist the legs together and throw it out, and then you've got a second LED in your kit. So grab that other LED and be really, really careful now so that you don't actually blow it. Okay. Now that we've figured out what the pot does and how it actually can impact your LED, we can actually use it to see what it does, what it's doing in the circuit to the voltage. So try and set up your circuit like this. So while the batteries are connected to the circuit, set your multimeter to measure volts in DC. Not AC, because this is not an AC circuit, this is DC direct current. So what you're going to do is touch the probes to either side of your LED. Try and hold the probes in place. So you might have to pair up with somebody beside you where one person can hold the probes of your potentiometer on the legs of your LED while the other person turns the dial of the LED. This is what it should look like. And this is what it's going to look like in the simulator. And you guys are going to try and do this yourselves. So you're going to take your multimeter, you're going to set it to measure voltage, not resistance. So set it to equal voltage. Now I've got the negative leg or the negative probe of the multimeter touching the anode of my LED. I've got the negative lead of the multimeter touching the cathode of my LED. Okay, so directly onto them. So what this is going to look like when I start my simulator is I am now getting a reading of the voltage. And if I turn the dial of my pot, you can see that I can go all the way down to, so if I increase the resistance of my potentiometer, my voltage is decreasing. If I decrease the resistance of my potentiometer, my voltage is increasing. And of course, I can go all the way to the end and blow my LED because I've just reduced that resistance right down to 0. You guys should not do that because it's going to cost you money. It doesn't cost me any money on this virtual Tinkercad. But you can see I can get to about 2 volts on that LED before it blows. So I'm going to set it back to the middle point so you can see it's getting 1.85 volts. So that's called the potential difference. That is the voltage that this component in my circuit is using. 1.85. So try and remember that. And then what we can do is actually measure the voltage, the potential difference of every component in the circuit. So the only other component really is the pot. So I'm going to measure the voltage that the pot is using as well. What do you think is going to happen? What do you think the reading is going to be? Some of you guys are brilliant and you've already figured this out. I'll be back with you in a sec once I've changed my circuit around. Okay, so here's what we're going to try and do now. We've measured the potential difference on the LED. Let's measure the potential difference on the pot. So if I move forward a slide here, notice how I'm going to change my multimeter to actually measure the wiper and the outside leg, the other leg that's in use of the potentiometer. So here's what it's going to look like in Tinkercad. I've gotten the circuit set up, or at least the multimeter set up onto the potentiometer instead this time. So similar to last time, remember we just had the multimeter set up on the LED to be able to get a reading of the voltage difference, or the voltage that is being used up by the LED. Well, let's see what the potentiometer is using. So if I start my simulator here, I can see that I've got 7.04 volts in use by the potentiometer. Now again, if I vary the voltage on the pot, I can see it go up to 7.10 all the way down to, well, next to nothing. But just before the LED blows, I'm down to about 6.5, 5. I can get down to about 5.8 volts or whatever before things go screwy on this simulator. So if I go back to the middle, which was roughly what I had on the LED, I've got a reading of 7.03 volts. Now if you remember what the LED, the potential difference of the LED was, I believe it was 1.85. So 1.85 on the LED, 7.03 on the pot. Well, 1.85 plus 7.03 equals what? 8.85, 8.88? Something like that? 8.88 is really close to 9 volts. That makes sense. If I've got 9 volts in my circuit, well, I should be able to find the measurement up. The voltage should be distributed throughout the circuit up to 9 volts because it's 9 volts. So 7.03, essentially 7 volts on the pot, essentially 1.85 volts on the LED, which means I've got a remaining 0.15 thereabouts volts somewhere, probably on the wires and the breadboard itself. So that's kind of cool. Once you've tested this with your circuit and are satisfied that you understand what's going on here, here's one of the fundamental rules of electricity. If you add the voltage used by all the devices in a circuit, in this case it's just a simple circuit with a pot and an LED, the total should be the same as the voltage supplied by the batteries, in this case, or the power source. So you measure voltage relatively between 2 points in a circuit. Okay, so if we know that voltage is relative based on where you are in the circuit, I wonder what happens to the current. So can we do the same type of thing and measure with the multimeter the current that's flowing through my circuit? The answer is yes, but it's a little bit more complicated because the only way that you can actually measure the current is if you insert the multimeter directly into your circuit. So I'm going to demonstrate this. I'm going to try. You guys don't do this because I'm afraid that if you do this wrong, you'll blow all the internal fuses of the multimeters, and that's a bit of a pain to switch out. So watch as I set this up. So you can only measure current when it passes through the multimeter. So that means we're going to insert it into the circuit. This is what it's going to try and look like. And I'm going to do this again in the virtual world of Tinkercad. You in this case, I don't want you to replicate this in the real world. Just watch what happens here. But we're going to try and insert the multimeter directly into the circuit by connecting it directly to the power, and the other side directly to the anode of our LED. And we're going to check to see how much current is flowing through the circuit at that point. So here's my virtual circuit. Not a whole lot has changed. I've still got my pot, I've still got my LED, and I've still got my wire that connects the two, the cathode to the wiper of the potentiometer. What has changed, though, is how the power gets into the circuit, because now I've got it being routed through my multimeter. I've got my multimeter set to amps, not volts or resistance, so I've got it set to measure the current, and I've got the positive terminal of my battery, I've got it going into through the positive probe of my multimeter, out the negative probe of my multimeter to the anode of the LED. So that's the change. Instead of power going directly to the anode of the LED and then power coming back from my potentiometer into the battery pack, I've got it being routed through the multimeter. So if I start my simulator, what I can see is now a measurement of the current. I've got 7.04 milliamps running through my circuit. Now if I play with my potentiometer, I can increase or decrease the voltage, which of course increases or decreases the current. Makes sense? So when I decrease the voltage, I don't want to blow my LED because that screws everything up. When I decrease the voltage, I can see my current gets reduced. When I increase my resistance, then the current, what did I just say? I think I just screwed that up. When I increase the resistance, my current goes down to 3.55 milliamps, so it gets decreased. When I decrease my resistance, then my current increases up to 28, etc. So I can make it go down to 3 and 4 milliamps, all the way up to 20 some odd milliamps. So let me set it back to about roughly halfway, or as precisely as I can at halfway, so I can remember. Oops, sometimes the simulator is a little bit funky. Okay, so good enough. That's close enough to the middle point. I think that's pretty much exactly at the middle. Close enough. So I'm getting a reading of 7.04 milliamps. So at this point, when I've got my resistance set to halfway through, it's a 2K ohm resistor. Oops, it's a 2K ohm resistor. So that's going to be at about 1,000 ohms of resistance. Then I've got 7.32 or 7. What do I have? 7, I need to get it set properly. So 7.04, I think that's halfway. 7.04 milliamps of current at 1,000 ohms of resistance. Okay, just like I was able to measure the voltage at various points in the circuit, and I saw the voltage was measured relatively based on where it was in the circuit, let's see what happens when I measure current at various points in the circuit. So I'm currently measuring current, that's kind of redundant, but I'm measuring current right now at the point between the battery and the LED. Let's see what happens when I measure the current at another point in the circuit. All right, here we are with our adjusted circuit. So same circuit, just the multimeter is plugged into a different point. So instead of the multimeter being right at the beginning of the circuit where it's going into the LED, before it goes into the LED, we're now at the end of the circuit when it's coming out of the pot. So now we've got power going in through the anode, out the cathode, through the wiper, out the terminal 2, into the multimeter, out the multimeter, and into the battery. So let's see what happens. So do you remember what the current was at the other point in the circuit, at the beginning point in the circuit? Let's start the simulator, and voila! 7.04 milliamps, which I believe is the same as it was on the other side, at the other point in the circuit. So this should be true at any point in the circuit. So this is very, very different than what we found with the voltage, because the voltage was different. The potential difference at each component in the circuit was different. So that means that each component uses a different amount of voltage. The potential difference, i.e. the amount of voltage that is used, is different based on where it is in the circuit. The current, though, the current looks to be exactly the same. So if I measure the current at any given point in the circuit, I should get the same result. So here's another truth, and as far as circuits go. The voltage is measured relatively. So the voltage changes based on where you're measuring the voltage in the circuit. So you remember that the LED used a different amount of voltage than the potentiometer. But now I'm measuring the current. The current's the same at both points, because I'm not measuring what the LED or the potentiometer are using. I'm actually just measuring how much current, how many electrons are flowing through the circuit at that particular point in the circuit, and it's the same. Now, what does that mean? Well, if you imagine this school going up in flames, and we're all trying to get out the same door at the same time, and there's 1,500 people in the class, or in the school, the slowest person in the school is going to set the pace. I could be Usain Bolt in here. I cannot get out that door any quicker than the slowest person. Why? Because we're all queued up. There's no place else for us to go. That's the same as the electrons in a circuit. The electrons can only go as fast as the slowest electron. That's being set by the resistance in the circuit. So if I adjust the resistance in the circuit, then I'm allowing my electrons to flow more quickly. If I'm reducing, or sorry, if I'm increasing the resistance, I'm reducing the speed that my electrons can flow every point in the circuit. If I decrease the resistance, then I'm increasing the flow or the speed that my electrons can flow at every point in the circuit, because they're all queued up. They're all in this little tunnel. It's like a hallway in a crowded school. They can't go anyplace. So this is the other truth here. Voltage is measured relatively, but current is measured in the same place. Wherever it is, it's going to be the same. It has to be, because the flow of electrons has no place else to go. So the current is the same at all points in a similar circuit. Voltage, the potential difference, is different based on every component in the circuit. Okay, let's do some math here. So what I'm going to do is I am going to remove the LED and substitute a 1K ohm resistor. So this is what the circuit looks like right now. So this is what it looks like in the virtual world of Tinkercad. We've got our circuit set up here. We have our pot still. We've got our, instead of an LED though, we've now got a 1000 ohm resistor. So the current's flowing through the resistor, in the wiper, out the terminal 2 of the pot, into the multimeter, and out the multimeter back to the ground side of the battery. So what does this look like when we actually start the simulator? So as I adjust the resistance of the potentiometer, I can see my current increasing and decreasing. That makes sense. But let's take a look at this. Let's actually take a look at this with a mathematical mind and see what you notice. So we've got a 9-volt power supply. So we've got 9 volts in the circuit. We have a 1000 ohm resistor and a potentiometer that can range from 0 all the way to 2K, 2000 ohms of resistance. So when I've got the potentiometer down to 0 ohms of resistance, it's essentially turned right off, then I've got 1000 ohms of resistance in my circuit, and that's it. And how much current do I have? I've got 8.98. Let's round that up to 9. So 1 times 9 equals 9. Interesting. Is that consistent? So if I go down to about the halfway point, so the halfway point of a 2000 ohm resistor means 1000 ohms of resistance. So I've got 1000 ohms of resistance plus 1000 ohms of resistance. So 2 times 4.5 equals 9. That's interesting. Again, if I turn the potentiometer, if I turn the pot all the way to max so that it is at 2000 ohms of resistance, 2 plus 1 equals 3, 3 times 3 equals 9. Oh my gosh! I've got some consistency here. So the resistance times the current equals the voltage. So, what does that mean? Well, I can do some basic math here. It's Ohm's law. You may notice that if you multiply the resistance by the amperage, you get 9 each time. Makes sense. I've got a 9-volt battery pack. So total resistance is 3000 ohms. Total current is 3 milliamps. 3 times 3 is 9. 2 kilo ohms of resistance produces 4.5 milliamps of current, and 1K ohm of total resistance produces 9 milliamps of total resistance. 1 times 9 equals 9. 2 times 4.5 equals 9. 3 times 3 equals 9. Ohm's law in practical terms. And you guys are all coming in at the end of class looking at me a little bit weirdly like I'm talking to myself, but I'm actually talking to you in this weird time warp.